we can't completely skip over the physics. We have to talk about a very simple concept. When you have a bond, you have atom A holding on to atom B in a low energy stable conformation. If I zap this thing with a lot of energy, for example, electromagnetic radiation, some of the energy will get absorbed into the bond, and this depends on the specific bond in question, meaning the atoms that are holding onto each other, how they're holding onto each other. But after they absorb the energy and jump to a really high energy level, the bond is going to release that energy because it wants to come back to a stable, happy, calm state. This right here is what we're looking at with IR. Every molecule is composed of all different types of atoms, and those atoms are being held together with all different types of bonds. For example, if I have a very simple molecule like methanol, I have the bond between carbon and hydrogen, the bond between carbon and oxygen, the bond between oxygen and hydrogen. I can add energy into each of these bonds, and they will turn and twist and bend in all different directions, but the amount of energy that they absorb is going to be unique to the type of bond that it is. And that is what we're looking at with IR. So we're going to hit it with IR, which is specifically infrared radiation. And when that gets released, the specific wavelengths that are tracked by the machinery, which for the sake of our sanity, we're not going to go through today, that is what we're going to study. So the basics of an IR graph. Let's draw just a simple one here. Ultimately, what we care about is what the heck is going on this graph and what does this tell us about the molecule. The x-axis is going to measure the frequency in wave number. I don't know that it really matters, but I'll put it here just in case. And the wave number, the Greek letter nu or the Greek symbol nu, is measured in units of per centimeter or centimeter to the -1. The graph will range from the number 400 on the right all the way up to 4,000 per centimeter on the left and everything in between. The higher the frequency, the higher the energy, the more exciting in terms of the graph. So here we'll have lower energy, and over here we have high energy. And typically in the high energy range, we're looking for the exciting functional groups, but let's hold on to that. We're going to come back. At the top, you'll sometimes see another unit of measurement there, and that is the wavelength in micrometers. But honestly, I've never had to look at this for a problem, so we're going to completely ignore the fact that wavelength goes at the top. And then what we have on the y-axis, that is the percent transmittance. And what this is telling us is if we're looking at the top, that means 100% is absorbed. 100% is transmitted. Nothing is absorbed. There's nothing there. The lower down we go, the higher the transmittance, the higher it's absorbed and then being transmitted. So, in other words, what we actually have to take away is the more stuff you see coming down, sticking down from the graph, that tells you there's something going on. Don't pay attention to the top. Look for what is coming down. Okay, again, we're looking at just the graph. I'm trying to take the physics out of it for now, just because I think that makes it more confusing. And so let's just look at what we have on the table here itself. Typically, and let me know in the comments if you are going to be given a table on your exam. Whoops, that got way too big. Or if you were told to memorize it. Now, I grabbed this one off Google. I think it came from the website Socratic.org. This is just a random table that you'll find in your textbook. And what this table tells you is the type of bond that you are going to see on your graph. on your IR graph, for example, this is a C double bound N, this is a C triple bound C, a C double bound C, you'll see about where it shows up on the graph. The wave number, that tells you where on the graph it shows up, and then the kind of intensity. So let's see where the comments. So again, let me know in the comments, were you told that you have to memorize them, or will you be given a table? Now, if you are given a table on your exam, I am going to challenge you that I still want you to memorize this. I still want you to know the information, but I don't want you to memorize it in a format like this. This right here is a lot of disconnected data that means nothing. It's a whole lot of numbers. And yes, for the MCAT, for the similar exams that you're taking, and a lot of organic chemistry students, I still recommend that you memorize it, but this is a mess. I want to show you a much, much easier way. I want you to memorize it based on image recognition, based on pattern recognition, based on something that you can actually picture and visualize and understand. So maybe that's a little bit too big of a graph. But what I'm going to do is sort of build that table with you. Instead of just a graph with numbers, I want you to see what it is we're looking at. We'll start at 400. We'll work our way up to 4,000. And let's just break it down. So we'll take 3,000, 2,000. Typically they go 1,500 and we're going to run out of room. So let's move this over a little. You'll see 1,500. You'll see 1,000. You might even see, yeah, that looks good. We don't need any other markings, any other numbers, any X and Y data information. Honestly, none of that matters. All I care about is what are you showing me on the graph? The first area that you're going to see and potentially get overwhelmed with is this. This right here, up to 1,500. This is called the fingerprint region. And the fingerprint region is very, very detailed. Here's how I want you to think about it. If you have to look at pictures of, say, family members or classmates, you can recognize different people by how they look, by their hair color, by their just different, very obvious characteristics. And you can also look at their fingerprints. But you have to know how to read a fingerprint. It's so detailed. It's so hard to see. It's a big mess. The fingerprint region is typically very, very busy with a lot going on. And it's so unique to each molecule that the difference between just constitutional isomers, think of butane and methylpropane, so 2-methylpropane and butane, isomers of each other, they're going to have a very different fingerprint region. Unless you're a scientist looking at this in lab, honestly, you'll have a computer, so you don't even need it for that. You're better off just ignoring that and looking here. This is where you're going to find all the useful information. So what is it that we're looking at here? There are two things. So what to look for? One, the functional groups that are present. And two, this is really, really helpful. What is not here? So let me explain what I mean. If I'm looking at, say I have an unknown reaction. I have an experiment that I followed. I have a general idea of where I'm going. And now I have a couple of graphs to identify the molecule. I see different things showing up on the graph, and I'm trying to figure out what the molecule is. In addition to saying this represents X, this represents Y, this represents, so on, I can also say, you know, I don't see that. It's definitely not this functional group. I don't see that. It's definitely not this functional group. If you look at any of my multi-spec videos, which I have in the Orgo Study Hall, a lot of what I do when I have HNMR and IR together is I use the IR to see what is obviously there and what is obviously not there. And then I go to HNMR to solve as much of the molecule as I can. And so you will get a lot out of recognizing what is obviously missing. Okay, so let's now take a look at what is here. I like to start at the 3000 range and just draw a quick, hopefully somewhat straight, not drunk looking line, because the 3000 range is going to give me a lot of information about the types of carbons that I have, but specifically here it's going to tell me the types of hydrogens. So what are the types of hydrogens that I could see on the molecule? I could have an sp3, and again, I'm looking at bonds, not atoms. An sp3 carbon bound to a hydrogen, so it's the carbon to hydrogen bond, but the carbon is sp3, compared to, say, an sp2 carbon to hydrogen. Again, it's the bond between carbon and hydrogen, but the hybridization refers to carbon, or an sp carbon to hydrogen. So let's look at some quick examples. If I have an alkane, I'd be looking at this hydrogen. Say I have an alkene like that, I'd be looking at, say, this hydrogen. And if I have an alkyne, I'd be looking at this terminal hydrogen. That is a mess. Let's draw that one again. So I'm looking at where on the graph can I find these hydrogens, and the 3000 line is the perfect area to spot it. So let's go back to the long way, and you'll see that you have carbon to hydrogen here, but it doesn't even tell you enough information. It just says 2700 to 3300. So if you memorize this, it did nothing for you. What we want to do is look at the ranges of exactly where they show up. If you go to the right, just to the right of the 3000 line, that's where you're going to see your sp3. What colors did I use for them? I did sp3 in green. So depending on how many you have, it can look something like that. And then again, this is the C to H, where that's an sp3 hybridized carbon. If you go just to the left of that 3000 line, I did that one in purple. I'm keeping it color coded so that you can follow. This is where you're going to see your sp2 hydrogens, or carbon to hydrogen bond. C to H, where the C is sp2. And if you shift over quite a bit, let me see what color I used for that. That's blue. There you're going to see your sp. So let's just kind of show something here. C to H, but that is sp. So looking at all of them together, what you want to do, mark your 3000 line. Immediately to the right of it, you have sp3 carbons holding hydrogens. Immediately to the left of it, you have sp2 carbons holding hydrogens. And somewhat shifted off, you have an sp carbon holding hydrogen. That'll typically be one, because if you have a terminal alkyne, you only have one hydrogen on there. If you have a benzene ring or something similar, it'll show up a lot more intensely, a lot messier, but still within that same region. So that is the first thing I'm looking at. Let me know in the comments if you're with me so far, if you have any questions on what we're talking about, and then we'll continue. When you're looking at these carbons, once you identify what you have or what you think you have, because sometimes you can't tell. What if the peak is right there? Is it an sp3? Is it an sp2? Is it an sp? You want to look elsewhere on the molecule to see if there's something else that helps back it up. If I have an sp3 carbon, well, the fingerprint region is where I'm going to see more information, and we are not going to talk about that. We're just completely ignoring it. But if we have an sp2 carbon, the carbon to hydrogen bond shows up around the 3000 line. The carbon to carbon bond will show up somewhere to the right. And that we do want to pay attention to. So the carbon-to-carbon double bond is going to be, I'll just put that here. So if you have the carbon-to-carbon double bond, this is around 16. Okay, so in your books, they give it to you the high number to the low number because left to right, but my brain wants to go from low to high. So we're just going to read this in an increasing number from 1600 to 1680. Around there, you'll see the carbon-to-carbon double bond, and this is the bond between the two carbons as opposed to the bond between carbon and hydrogen. These will be kind of skinny, kind of pointy. Where is my graph? Here. Kind of skinny, kind of pointy, around 1600. So let's show it looking something like this. But, okay, so that's your C double bound C, but let me show you another one. If you have an aromatic ring, if you have benzene, technically that's carbon double bound to carbon, but quite a few times, and the aromaticity is going to make it show up just differently enough, still around the 1600, but also somewhere around 1400. So this is one thing we do look into the fingerprint region. And around 1400, you're going to see something like this. Those are your skinny fingers. You're looking for two between 1400 going towards the 1500 range, and then you'll also see something close to 1600. Your skinny fingers tell you that if I have the carbon-to-carbon double bonds, there's likely an aromatic ring in there. If I have the sp, the carbon-to-carbon triple bond, this time I want to look at the bond itself. Because it's a triple bond and can absorb so much more energy, it's going to show up much, much higher. This will be from 2100 to 2260. And that would be almost connected to this, but not quite. So you'll see a peak that kind of looks like just something that sticks down. Like that with a little bit of messiness next to it. So this, again, if you recognize you have a carbon sp holding a hydrogen, look for this to back you up. So you're not looking at something in isolation, you're trying to find something to back you up so that you can see, oh yeah, this is kind of what I was looking at. This is justifying that I identified that functional group. This is very similar to having a C triple bound N, which would also show up about here. So you have a C triple N versus a C triple C. And so this is where you want to look at what else you have on the molecule, or if you're given a molecular formula, or if you're given NMR or something else to back you up, if you can't fully tell them apart, because sometimes they are quite confusing. Once you identify the kind of carbons that you have, we are going to need a lot more room for this. Let me try something. I don't know what just happened. I didn't know I can stretch it like that. Okay, let me just move it. I'm just trying to give us more room in this area because we're going to need a lot more space for all the functional groups. Which functional group are you most comfortable with on the IR graph? The functional group that I think most students are familiar with are the ones that have oxygen in them. And those are the ones that I look for in the exciting area as partly knowing what do I have or what do I obviously not have. Let's start with an alcohol. Instead of constantly jumping back to that table, I'll just give you the numbers. If you look at the bond between the O and the H, not the C to the O to H, this will show up somewhere in the 3200 to 3650. You memorize this, you're toast. It is such a big range. And let's actually go back to that table for a moment. What did they give us for the alcohol? Strong, very broad. It doesn't tell me much. I need to see it. An alcohol is typically the most left functional group that you're going to see, and it's going to have a nice big curve. This is how you tell the alcohol from other functional groups that show up here. So that's the O to the H. If we have an amine, it shows up in a very similar area. An amine, you'll remember we have a couple of different types, but the N bound to H could be a primary, secondary, or tertiary. And this shows up, well, pretty much the same area, 3,300 to 3,500. So how do you tell the amine from the alcohol? The amine is going to be a little bit more pointy, and it's going to also tell you how many H's you have on there. Because let's say I have a secondary, let's say I have an amine with two hydrogens. So for example, I have an N, H, H, and then an R group. These two hydrogens will give me the double peak. If it was just NH, for example, CH3 2NH, then I would have only seen the one. But also notice the difference in the shape from the alcohol being broad and just nice and round. The amine gets a little bit pointy, and that is how you can tell them apart. Another one that shows up here is also an OH, but this one is a carboxylic acid. And specifically, we're looking at the bond between this O to this H here. So it's very different from the alcohol because the carbonyl is nearby, and having that carbonyl also absorbing energy nearby is going to completely change the shape. And so a carboxylic acid is going to look almost like an amine and an alcohol put together. Oh, I forgot to give you the numbers. So the range for the carboxylic acid is 2,500 to 3,300. It's a very, very big range, and it could mess you up if you're only looking for the numbers, because now you're looking at this entire area. Unless you think, okay, I'm looking for a shape that kind of looks like that. So it almost looks like an alcohol with like something sticking out of it. And I'm showing you different shapes because you'll see a little bit of all of these like that. So that'll be the carboxylic acid, specifically the OH bond. What else would these functional groups have? If we have an alcohol and we looked at just the O to the H, let's go back to the alcohol and see what else we expect to find on the molecule. The C to O, and I should take out alcohol because this could be what other functional group will have a C single bound to an O? This is another exception to the fingerprint region because it shows up in the area of 1050 to 1250. Again, we hardly ever look in the fingerprint region. This is one, and the skinny fingers for a carbon-to-carbon double bond or aromatic ring is the other, and that's it. So around the 1000 range is where I'd be looking for the alcohol, and it would look something like this. Let me change that so we don't get confused. And I'm going to take out this right here so you can see what I'm actually looking at. I'll put it in like that, kind of like background noise. There we go. So that's it that we're looking for in the fingerprint region. Are you with me so far? I know there's still a couple more to look at, but how do you feel about studying a graph like this versus studying one like that? Which one would you rather if you have to memorize them for your exams? I know that was a trick question because I know what I'm hoping you're going to answer, but I'm curious what you think so far. Now, while you're typing that in, the carbon to nitrogen is also going to show up around here, but it's not one that you want to go looking in the fingerprint region for because it's not as obvious and not as easy to recognize. All right. So I see ester, that is one, C to O. Alcohol, that's another. Carboxylic acid is another. And what I'm not seeing is an ether. An ether is just C to O without having the alcohol. So if you identify this right here, but you don't see the alcohol all the way on the left, you probably have an ether. As for which one, Catherine, I agree with you. Pictures are so much better to visualize. Siva, yes, they speak 1,000 words. Jerome, absolutely. So let's take a look at a few more. Another family of functional groups that you're going to see are the carbonyls. A carbonyl is a C double bound to an O. What functional group has a carbonyl in it so that we know what we're looking for on the graph? The carbonyl is going to show up between 1650 to 1780. So I like to look around 16 to 1800. In my mind, that is an easier number to memorize, and it's still within the same area. And within this range, sometimes you'll be asked to differentiate between two functional groups that both have a carbonyl. The lower range is going to be something that has additional resonance, something to distract the electrons. What do I mean by additional resonance on a carbonyl? And it's going to be higher if it stands alone. Well, I guess first it would help to understand which kind of functional groups we're looking at. Ketone stands alone. Aldehyde stands alone. Absolutely correct. And so this would be, I'll put it here. So a ketone is in the middle of a molecule, and aldehyde is on the terminal end of the molecule. And then we're looking at groups that have something else next to it that will resonate onto the carbonyl, changing the way it can absorb energy. That would be your carboxylic acid and your carboxylic acid derivatives. So I have an ester, an amide. These are the most common ones that you're going to see. So these are going to be on the lower end. And let me put the arrow in green so you can recognize the functional groups that match up. And then these are the ones that stand alone. So I'll put the arrow in orange again so you can recognize. The way it shows up on the graph is also very, very distinct. So the 16 to 1800 range, but it's going to show up. So let me show you again. I put in orange for the higher and green for the lower. I just want to make sure everything matches up for you. So it's going to show up something like this, but it's got a nice broad, it doesn't come to a pointy, skinny tip like we saw with a lot of the other ones. I'll just put the one here, but recognize that all of the carbonyls will show up like that. Question. Ketones tend to be higher wavelength. So it's not about the wavelength of the functional group. It's what you're looking at on the graph is if you zap this thing with energy, the bonds will take in energy, hold them for a fractional amount of time, and then release it. And when the energy is released, the machine will read the wavelength that it gets released at. And the slightly higher range between 1650 to 1780 tells us that it's likely the ketone aldehyde. But if it's in a slightly lower range, closer to 1600, it could be your carboxylic acid, your ester, your amide, and so on. It's not so much about the resonance for the sake of resonance, but rather for how having that group there impacts the electronegativity, the way the bond holds, the structure, the way it can absorb energy because of this conjugated system. So Jerome, that was your question, and I hope that makes sense. And for this student as well, I hope that also makes sense. All right, for the problems that we're going to work on from here forward, I am going to refer to this rather than this because I'm not interested in the numbers per se. I'm interested in making sure you understand what is going on here. So your first homework assignment is, as you're studying, even if you're going off a table like this, I'm going to challenge you to go to Google and put in examples. So if you're looking for C to H, put IR graph methane, IR graph ethane. So instead of memorizing this number, I want you to see a bunch of different graphs. And when you do that, you'll notice, for example, that some alcohols look like this, some look like that, some look like that, some look like that. But if you can see the same functional group, an alcohol, show up on a phenol, show up on a straight chain, show up on a branch chain, and you see how it changes a little this way, a little that way, what you're memorizing long term is a series of related images that make sense to you, as opposed to a static number that means absolutely nothing. So now that you know how to study them, let's start working through them together. So let me know in the comments if you're ready to put this rather than the numbers into practice. And don't forget to try this on your own after we're done. Make sure you sign up to get a copy of today's notes and the worksheet at layforsi.com/orgolive. Okay, so I prepared a couple of drawings for us to work through. Let's start. Oh, hang on. I have to figure out how to grab them. Here we go. So here's what I want to do. I'm going to tell you the molecule afterwards because you're not going to be able to simply look at this graph and figure it all out. Instead, I want to look at the graph with you and try to understand what we can tell and then accept where we have to just take a step back because you're not going to be able to decode this entire thing. The first thing I like to do is identify the 3000 range and see what I have going on there. And you'll notice that I have the peaks happening both to the right and left of the 3000 range. We know that to the right of the 3000 range, and my line is a little drunk, but we still have peaks on either side. We know that this is going to be C to H bonds with sp3 carbons, and directly to the left of it is C to H bonds with sp2 carbons. So we know we have some potential pi bonds going on here. And as soon as I identify sp2, I want to verify somewhere else on the molecule. So where else would I look? Where did I have that thing drawn? Here. Where else would I look for the carbon-to-carbon double bond to justify my sp2? That's this one right here. And we said it's around the 1500. And again, notice I'm not using exact numbers. It's around the 1500. But if it's an aromatic ring, I also have the skinny fingers even lower down. So do we see any of that here? That right there is my 1500 line. I have a very definite and obvious peak here, telling me that I likely have, justifying that I have my carbon-to-carbon double bonds. But then under 1500, because the skinny fingers show up around the 1400 plus range, I have 1 and 2. What do the skinny fingers tell me that I have? It's very likely an aromatic ring. What else do I have on this molecule? I have a whole lot of I have no idea and don't care because this is the fingerprint region. I kind of feel bad that we have nothing here given how long it took me to draw all that out, but nothing doing. It doesn't tell us anything. I then look for my obvious functional groups. I have a little bit of noise here, which is very, very common. You're going to see a lot of noise on the graphs. This depends more on the machinery and how clean everything is and how some machines are more accurate than others, rather than what else is going on there. But I don't have anything obvious. I have no alcohol, I have no amine, I have no carboxylic acid. A couple of things that I could find here, like a triple bond, a nitrile. I definitely don't have a carbonyl, which would have come down very intensely. This right here is all noise. Sure, it means something, but not at the level that we're looking at and not something that we potentially have to understand. So as far as this graph is concerned, that is the information that we have. We have a benzene ring and some additional carbons on it that are not sp2 hybridized. Typically with this, you'll be given some other information to help you figure out what it is. But since this is all I gave you, the actual molecule looks like this. A benzene ring with an ethyl group on it, and that's it. What do you think? Do you agree with everything we picked out, and do you feel comfortable with what we picked out and why? Question. For example, we would never see a free OH around 1400 to 1000. It is usually above the 3000. If you're asking about an alcohol, then it would show up here, and then we would also find something in the fingerprint region. If you have something in the fingerprint region for the C to O, but nothing here, it's not an alcohol, it could be something else. But you're asking specifically about the OH? No. Okay. So your question on the OH itself, what you see in the fingerprint region would have been just the C to O. So this is the alcohol carbon bound to oxygen. So the alcohol or the ether, basically whatever C single bound O that you have. Here is where you see the O to H rather than the C to O. Question. Wouldn't the benzene ring be between 1200 to 1000? So if we look at the numbers itself, the benzene ring, I crossed it out, but it's showing 1430 to, I think the number is 1600, under 1500. So the skinny fingers are just under 1500. There is more. Let me clarify. There is more in this region that tells us there is a benzene ring here. And if you plug this graph into a computer that is very capable of reading the fingerprint region, that computer will give you your final molecule without a doubt. But for what you have to be able to identify with your own eyes, pen and paper kind of exam or computer type of exam, this is all you need to know. Does that make sense? There's a lot more information, but not something that's possible to solve at the level that we're trying to do. So let's try another one. And for this one, once again, let's start with what it is that we see, anything that we obviously don't see, and then come up with a molecule itself. Let's start at the 3000 range. What do I see? The peaks coming down. They're coming very low. It doesn't really matter if they come down like this or all the way down. Also, I should point out, I'm saying peaks. These are technically troughs or valleys because they're coming down. Peaks would have gone to the top, but I'm imagining this is an upside down peak. To the right of the 3000 is where I see a lot going on. And this tells me that I have carbon to hydrogen, where the carbon is sp3. Also very, very obviously standing out on this molecule. Look at that nice, big, broad, not pointy peak or unpeak, opposite of peak, coming down. This right here tells me that I have an alcohol, specifically the O to H. And knowing that I have an alcohol, let me jump on over to somewhere near the 1,000 range and see, oh yeah, this is likely the C bound to O from the carbon that is holding the alcohol. This right here, no idea, it's noise. All of this, no idea, it's noise. It doesn't matter. We don't need it. That's pretty much it. That's the information that we got here. Yeah, that's all we need. Okay, so the molecule ultimately is cyclopentanol, which, as you can see, is just a ring of sp3 carbon atoms bound to an alcohol. Trying to see which one to do next. Let's do this one. If you have questions so far, let me know. Otherwise, I will grab the next graph and I want you to tell me in the comments what it is that you see, what you think we have here. I'll give you a moment to work on it. Okay, let's do Q&A while everyone's thinking about it. Question: how do you know it's a ring and not a chain of carbons? That is a very good question. And the answer is, at the level that we are studying IR, you don't. Some students at the very advanced spectroscopy level will have to learn that, but 99% of my undergraduate organic chemistry students do not need to know that. For the MCAT, you absolutely don't need to know that. If they gave you an unknown and it's multiple choice, you wouldn't be given the choice between, say, a pentanol and a cyclopentanol unless they gave you something else with it. So let's go back to the last question. Let's say here you did have a choice between something that looks like this. But in addition to giving you the graph, they also gave you a formula of C5H10O. Now you would use this formula to solve for the index of hydrogen deficiency. And in this case, let me remind you, the formula is CnH2n plus 2. I have a video on this if you need to review. It's on this YouTube channel. Our N value is our carbon, which is 5. And so we solve 2n plus 2. 2 times 5 plus 2, that's 10 plus 2 equals 12. What am I jumping ahead of myself? 10 plus 2 is 12. We only have 10. So 12 minus 10 is 2. Divide that by 2 equals 1. We have 1 degree is equal to our index of hydrogen deficiency. This tells us that I have 1 pi or 1 ring. And because we know we don't have any pi bonds, given that we don't have anything showing up on the graph to prove a pi bond, we know that it's a ring. So do you see how it's not the graph itself that gives you the final answer, but something else within the question, either a molecular formula, you can have mass spec, you can have HNMR. I mean, HNMR would be a dead giveaway in a situation like this. So they'll give you something else to help you solve it. Okay, so going back to the next one. Jerome, you are correct in guessing that we have a carbonyl. So this right here, notice that it's not as broad as I've shown you before, but it's also not coming to a point. The carbonyls tend to be more curved, more nice and round. So we know we have a carbonyl. What else do we have? Don't just look for the exciting things, look for the simple justifying your molecule. So let's start with the 3000 line. And on the 3000 line, again, my orange line going up is not perfectly straight, but you'll notice that most of this peak is sitting just to the right of it. And this tells me that I have carbon dihydrogens sitting on an sp3 bound carbon. Everything to the left of it is kind of high. So it looks like there's a lot of noise there, but not necessarily enough to give me information that, hey, there is a peak here. I have a carbon to oxygen. Typically, you then look here to see if there's anything else. Because if I had this kind of shape, but all the way down here, I would wonder if I had an amide because of the NH, a carboxylic acid because of an OH. But I'm not seeing that. And so there's no reason to go to the fingerprint region to look for a C single bound O. Well, actually, there might be if I suspected an ester. But in this case, there's nothing obvious. I mean, I see that. But again, we don't want to start digging in the fingerprint region if we're not sure about what we have there. So let's just cross that out. I obviously don't have C to C pi bonds, meaning double or triple bonds. I don't have an alcohol. I don't have an amine. I don't have a carboxylic acid. I don't have any of that. This right here is mostly noise, nothing exciting here. And there's a lot going on here, but because we had nothing here telling me, justifying that I need to look to the right, I'm not going to, because fingerprint region, it's a mess. That's a bigger region right there. So we're going to ignore all of that. The actual molecule in question here is 2-butanone, which looks like this. And as you can see, all it has are 3 carbon atoms that are sp3 hybridized and 1 carbon that is sp2. But remember, this is the carbon to hydrogen bond. That sp2 carbon, the carbonyl carbon, does not have hydrogen. It only has oxygen, and that's the carbonyl. And notice that it's showing up quite higher, quite shifted to the left of the 1500 because it's standing alone rather than having another electronegative group next to it. Question. If you find the degrees of unsaturation, you can identify what components are a part of the molecular formula. The degree of unsaturation, if I have a formula in a multi-spec problem, that is the first thing I solve for, because even though it doesn't give me anything specific, it helps me know to look out for a pi bond or a ring. In this case, my degree of unsaturation would have told me I have a pi bond or a ring. And then as soon as I notice this right here for the carbonyl, I feel validated. Hey, I suspected a degree of unsaturation. I have a carbonyl. I confirmed my degree of unsaturation. But it's not enough to give me the specifics because I have no idea just from the degree of unsaturation if that's a ring, if it's a carbon to carbon double bond, if it's a carbon to oxygen double bond. So I would need more information. And hopefully this comes along with an HNMR graph, because HNMR gives you the absolute most information. Question, how would you know if the C double bond O is connected to a benzene ring or not? That is a really good question. And again, an advanced question. It's not something you have to know at this level, at the undergraduate organic chemistry level, at the taking an MCAT or similar exam level. In order to answer that question, so you're asking about, let's jump on over here. You're asking, how would I identify if I have, say, a benzoic acid? I would see the carboxylic acid. I would see the carbonyl. I would see the benzene ring. I would see that I don't have any sp3 carbons. Actually, if all you had was this and a formula, meaning if you had IR and a formula, you could figure it out, because if you have nothing else, just a carboxylic acid and a benzene ring, the only way to put it together is to attach them. But if you had something more going on, you would need additional information, like typically you'll see we carried out the following reaction and this is what we got. Or you would see something like, here's the HNMR next to the IR, and now use both of them to solve it. Question, even in OChem 2, you won't need to know a ton about these things. No, for organic chemistry 2, all you need to know for IR is what I showed you here. And where I told you you don't have to worry, you don't have to worry. IR is typically just to help you identify what functional groups are here, what functional groups are obviously not here. And then the rest of the question, the other graph, the formula, whatever else your professor gives you, is how you're going to solve the rest of it. So, for example, a very common question that you're going to see is, here's a graph. Here are 5 molecules, molecule A, B, C, and D. Which one corresponds to the graph? And I think I showed you something with this one, right? So let's say you had this plus 3 other choices. You would look at each of the molecules given, each of the choices, and look at the graph and ask yourself, which one can I very obviously rule out and why? And in a question like this, you would assume that you have a formula. Or if you weren't given a formula, maybe this one was given with a pi bond. And now you can say, okay, so they both have an alcohol. I see that here. They both have sp2 carbon holding, sp3 carbon holding hydrogen. I see that here. But this one has sp2 carbon holding hydrogen. I don't know if I see that here because it's such a mess with the alcohol. I can't tell. But then I look on over at the 1500 range, and I don't see anything coming down for a little off the 1500 range. I don't see anything coming down telling me that I have that pi bond there. It's probably this one. That's how the questions would be presented. Or multi-spec. That is how your professors really like to do it. Here's IR, here's NMR, here's HNMR, CNMR, mass spec. Go figure it out. All right, so we looked at a couple of different ones. Ultimately, I want you to walk away with an understanding of this. I have 2 more graphs, like the problems I showed you here, on the worksheet so that you can try to see what functional groups you have present. I'll throw the molecules down on the page below so that you can try it before you peek. And on that worksheet, I'll also include a couple of, do you think it's this or this? How would you tell them apart? And the way to get that worksheet is very simple. Just go to, why is that not working? My thing froze. Right here, layerforsci.com/orgolive. That's where you'll get a link to this recording, the worksheet for today's session, and a copy of the session notes, everything I did here. For even more on organic chemistry, because today was just a beginner topic of IR. But if you want to see this in practice with multi-spec, where you're given a molecular formula and 4 different graphs, HNMR, CNMR, IR, mass spec, and you have to use all 4 of them together to come up with a molecule from start to finish, I have quite a few videos on this with multiple problems in each, taking you through it step by step with what I'm looking at and how I'm solving it. All of this and more is part of my Organic Chemistry Study Hall membership site, and full details and link to sign up is at layerforsci.com/join. In addition to the multi-spec and just more on spectroscopy in general that I mentioned, the Organic Chemistry Study Hall has, well, the YouTube lives that I'm doing are beginners. We go deep into the beginner understanding of a single topic. But in the study hall, you'll get the more advanced videos, the more advanced practice, the more advanced lessons on everything Organic Chemistry 1 and Organic Chemistry 2. And in the study hall, you also get to join my members tutoring and support group where you can post your daily study questions. And that way, it's not just here's the information that I'm choosing to teach today, or here's the information in the video, but you actually get to ask me questions on what you're stuck on, the quiz that you're studying for, the upcoming exam, your homework, something that you don't understand, so that I can help guide you, myself and my TAs can help guide you in more detail, and so that you're not feeling alone on this journey. So the link to sign up there is layerforsci.com/join. And with that, everyone, have a wonderful rest of your week. See you next week for a topic that we will choose over the weekend, and have a wonderful day.